Okay, welcome to this series of videos in which we've already talked about angular motion, angular kinematics, I should say. We've already talked about torque. We're going to review those very briefly, and then we're going to get into rotational dynamics. What rotational dynamics is looking at systems in which objects not only move rectilinearly, but also there is an angular component to that as well. So we'll actually, in this set of videos, we'll actually review a type of problem that you learned how to solve a long time ago and kind of do just that next level. Okay, how can we make this model that we have more accurate? So before we get to that though, we will start by reviewing torque. Remember that a torque is a rotation of an object as a result of a force being applied. Really, I probably should say twisting or turning instead of a rotation of an object, because when we have objects rotating, you could just say, well, isn't that circular motion? No, it's a little bit different in this case. So a twisting or turning of an object as a result of a force being applied. The size of the torque that is exerted is affected by a few things. The first is the magnitude of the force. If you have a bigger force, that's usually going to lead to a bigger torque. The second is the distance that the force is applied from what I'll call the axis of rotation. Okay, that matters. And the third is the angle between R and F. Because remember, the equation for torque, this is a tau, that's a symbol for torque. Tau equals R F sine theta, okay? R being the distance that the force is applied from the axis of rotation. A bigger distance from the axis of rotation means a bigger torque, more twisting or turning action. A bigger force leads to a bigger torque, and depending on the angle, that can also change the size of the torque. Since it's a sine, if the sine of 90 would be the biggest possible torque that you can have, which means that R and F should be perpendicular to one another. In other words, wherever the line is from the axis of rotation to the place where the force is being applied, in order to produce the biggest possible torque, you want to put your force perpendicular to that line. Torques can either cause clockwise or counterclockwise rotation. Typically, it's convention for us to say that counterclockwise is positive and clockwise is negative, but that changes depending on the system that you set up. And then lastly, if you have many torques that you're dealing with, you sum them up just like you would net forces. Net torque equals T1 plus T2 plus ... for however many torques that there are. And that's equal to I alpha. Very similar to the net force.
The delivery down by the shop area.
Okay.
It's a large delivery on the south end of the building. That is deliveries at the south end of the building by the shop area.
Let's move on to angular motion. Angular motion is essentially you're dealing with the same equations as linear motion. But with angular variables. Okay, so we've before that interruption, we've talked about torque. That's pretty much everything we have to do to review torque. Angular motion, or angular kinematics might be another name for it. You have studied kinematics before. You're very, very good at kinematics, angular kinematics is pretty much the same thing, except instead of measuring how far something moves or how fast it gets from point to point or what the linear acceleration is, now we're measuring what angle something has rotated through or how fast it's rotating or the rate of change of this rotation. So we have, I'm just going to list a whole bunch of equations and show you their angular counterparts. We have our definition of linear speed or velocity, v equals d over t. And I know it could be x minus x naught over t, but just bear with me. Or actually, we should have some deltas in front of this to show that speed is the change in distance over the change in time. When we talk about angular variables, we're not talking about linear speed anymore, we're talking about angular speed, given by this symbol omega. And angular speed is given by the change in angle, the angle that something rotates through, over a certain period of time. And our three basic kinematics equations change in a similar fashion. So we see already that that linear speed, v, basically is equivalent, or not equivalent, but it's analogous to omega. We see that d is analogous to theta, or I guess you could also say x is analogous to theta. Some of our other equations, here's one of the kinematics equations, x equals x naught plus v naught t plus 1/2 a t squared. It's the exact same equation we're dealing with angular kinematics, but the variables are switched in some cases. So now we would have theta equals theta naught plus omega naught t plus 1/2 alpha t squared. By the way, the units for these new angular quantities are not measured in meters, since we're not measuring distances or displacements, we're measuring angles. And these angles are measured in radians, not in degrees. So one thing to watch out for is that in, let's say, the torque equation, we do expect you to use 90 degrees here, or 0 degrees, or 180 degrees, or whatever. But when we deal with these kinematic variables like this theta, when it's representing how much of an angle something is turned through, or omega or alpha, we do expect those angles to be measured in radians. Let me just fill in the last couple of equations, and you can see how they're analogous equations in angular kinematics. Let's see, v equals v naught plus at would be omega equals omega naught plus alpha t. And then lastly, v squared equals v naught squared plus 2a x minus x naught becomes instead omega squared equals omega naught squared plus 2 alpha theta minus theta naught. And there are a set of equations that do allow you to convert from what I would call linear kinematics to angular kinematics, one of which you learned way back in geometry class a long time ago, and that is S equals R theta. S being a distance, you can remember this is like the length of a distance around the perimeter of a circle, is equal to R, the radius of that circle, times theta, which is the angle in radians that is contained by that arc on the perimeter of the circle. Okay, so we can convert back and forth between a linear distance measurement and an angular distance or displacement measurement. If we divide both sides of this by t, we end up with this other useful equation, v equals r omega. And if we divide by t again, we get a equals r alpha. So those are ways to convert between angular measurements and linear measurements. Now let's talk about something that we have mentioned before very briefly, but I don't think we wrote a ton of notes on it. I think I more or less demonstrated it for you, and that would be moment of inertia. The best definition, what you need to know about moment of inertia, is that it shows you how hard it is to rotate something. Okay, just like mass, it's kind of it's analogous to mass. Mass is how hard it is to get something to accelerate, to linearly accelerate. I guess you could think of moment of inertia as being how hard it is to get something to have an angular acceleration, which is essentially how hard it is to get something to rotate. And this is based on the shape of the object and the mass of the object. So unlike with linear dynamics, where the amount of acceleration was only dependent on the size of the force and the mass of the object. In angular motion, how hard it is to get something to rotate is dependent both on the shape of the object itself and on its mass. So the first thing I want to talk about is, let's say that we have, let's say here's our axis of rotation, and we just have like a little, a particle of mass right here. You might want to know, okay, well, if I want to make that revolve or twist or turn or spin or whatever around that axis of rotation, what would the moment of inertia be for that? How hard is it to get it to do that? And the answer is that I, for what we call a point object, in other words, an object that can be reduced down to a point without losing any, basically your spherical objects that can be reduced down to a point without, making gross changes to what's happening. I, for a point object of mass m, revolving a distance r from an axis. So we've got this point mass, it's r away from the axis, and it's spinning around this axis. So you can imagine the point mass maybe right now is moving into the paper, and then it kind of comes over here, and then it comes up out of the paper on the other side, and comes up above the paper, and then goes back in, and it's revolving like this, okay? The equation for the moment of inertia for a point object like this of mass m revolving distance r from the axis is as follows. I equals mr squared. And yes, that is one equation that you do need to memorize right now. That is an equation that would be a good idea to memorize. Okay? So that's for a point mass. If you have some extended object, your moment of inertia will be different. So for all other shapes, unless you can count it as a point mass, and we'll look at examples where you can count things as a point mass and where you can't. For all other shapes, I is equal to, I'm just going to put b times mr squared, with b as a coefficient and r as some significant distance. So essentially what this means is that for any other shape, let's say you have maybe a sphere, not a point anymore, but a sphere rotating about some axis. Let's say you have a thin rod or a hoop or a disc or a hollow sphere or a rectangular prism, something like that. For any of those types of objects, the general formula for the moment of inertia will still look like this. I equals b times m times r squared. The only difference between this and the point mass is that there's just some coefficient out in front of it. That coefficient might be 2/5, might be 1/2, 1/3, 1/4, 1/12. It depends on the shape. There is actually a way to derive what the moment of inertia is for any particular shape, but it involves calculus, and that's beyond what we need to do in this class. So we're not going to do that, okay? This might sound a little intimidating. You're like, well, how do I know which one to use? Do not worry. Do not memorize the formulas for all these different shapes. You do have to memorize this one, but don't bother memorizing the formulas for all the different shapes. Do not memorize formulas except for a point object. The reason you don't have to memorize them is because they will be provided. Didn't used to be like that. Okay, it didn't used to be like that, but thankfully they will provide those to you now. The last thing I have to talk about with moment of inertia, okay, remember all it means is just it's how hard it is to get something to rotate, how difficult it is if you have an object with multiple parts. Like let's say that there was another point mass over here and they were both revolving, okay? For an object or system of multiple parts, to find the total moment of inertia, It's just the sum of all the little individual parts. I total equals the sum, that's a symbol for sum, remember, of I parts. So you can break something down into basic shapes, and then you can look at the moments of inertia of all those different shapes and pieces. You add them together, that would be the total moments of inertia. Okay? There's only a couple times where you have to do that, but it is a useful thing to know. We're actually not going to talk about angular momentum right now because we talk about that in a future video in more depth, so you can cross that out. The last thing I want to point out before I get into an example is the idea of rotational kinetic energy. You guys are used to kinetic energy. You know objects have kinetic energy when they move, but you probably haven't thought about the fact that an object that rotates also has kinetic energy. And you might say, well, wait a second, that object's not moving from place to place, but the individual pieces of that object are rotating. So we do still, that object, parts of it are still moving, so that object must have some kinetic energy. So rotating objects have kinetic energy, even if they are not translating. And translating is just a very fancy word for moving linearly. Even if they're not translating. Okay? We know that the equation for translational kinetic energy is 1/2 mv squared. The rotational kinetic energy equation is actually very similar. K rotational equals 1/2 I, so it's almost like we're just replacing mass for I, omega squared. Okay? So there's our equation for rotational kinetic energy. And it is possible for objects to have both translational kinetic energy, which again is given by 1/2 mv squared, and rotational kinetic energy, 1/2 I omega squared, at the same time. They can have one or the other, they can have neither, or they can have both. Okay, anything goes. The example I guess I give would be for rolling objects, which we will study in a couple videos. Okay, so there's a quick kind of recap or quick little mini lesson on everything you might need to know about torque, about angular motion, about moments of inertia and rotational kinetic energy. You at least know enough to be getting on with now so that we can start to look at some problems that, basically some forces problems that we looked at a long time ago that we're now going to look at in more detail and make it a little bit more realistic. I'll be back with that video in just a little bit.